Okay, this is video number 4 of exercise 7 in chapter 4 of the Advanced GIS textbook. In this video, we're going to be looking at visualizing geologic principal component analysis for the Black Rock Desert, following up on having run the PCA and looked under the hood a little bit at the output tables from the principal component analysis. This video will not actually physically map things, but will visualize using the geologic band ratios and the PCA and compare to existing geologic maps for the area. And so this will be a little bit long of a video, more qualitative visualization. So here, the first thing I've shown is the principal component analysis VRD PCA open in a stretched mode, so it can only display one band at a time. And I did this for a couple of reasons. First, band 1 looks kind of washed out in this view. And this is important to realize that what you look at is all dependent on how you're visualizing the histogram. Right, so we can see that basically what we've done, right, is the histogram, most of the values are here around a value of 3 in this principal component PCA1 units. And we've trimmed, I guess, 0.5 off of either side. It's not looking too good, right? So if we change this to standard deviations, it's going to look better immediately. Okay, so now we're going across, we're stretched all that out across there. And now we see a lot more detail. But, you know, we probably stretched it out more than we need to. And so if you go to 1 standard deviation, it's going to look even better. So now we can see kind of bigger contrasts between the grayscale for PCA1 or PC1, principal component 1 of the PCA analysis. So as it's suggested in the data table, that first principal component layer number 1 accounts for 72% of the variance across the data set with all those band ratios. And so with this black and white image, we're seeing up to 72% of the variation in terms of the soil band ratio kind of difference across this Black Rock Desert. And indeed, we can distinguish like the lake from these alluvial fans. And even within the alluvial fans, we can see that there's differences, right? Some are darker and lighter, suggesting they have different soils and different underlying geologic origin. And then if we look at the volcanoes, this volcano, Pavant Butte, is a little darker than, say, Tabernacle Hill down here, which is covered in weathered products because it's older and was erupted under the lake, whereas this was subaerial. Here's another old volcano, slightly light, but then we have the younger volcano here. And on top of that, we have all these aeolian deposits. So we can see a lot with band 1 or principal component 1 of the PCA. I can go to principal component 2, and you can see right away that there are some areas that show up more bright or more dark. So it is definitely showing us something different. We can't see as much disparate details across the landscape, but some areas are teased out a little bit differently. So like if we look down here at the most recent lava flows, you know, they very distinctly show different than this one right here, or that one right there. So there's quite a bit of value there. So I'll go back and forth though to print to 1 again. But the value isn't quite as good over the whole image. If we go to principal component 3, now things maybe look kind of interesting over in these mountains here, but maybe it's dark over large parts of the region. But on the other hand, you can see quite a bit of distinction between like the rocks and the vegetation. So take that what it is. If we keep going, if we go down to 7, give it a minute here. And I should have suggested we kind of go and look at whether or not they've got both pyramids and statistics built for in the geodatabase for these data sets so they load faster. Okay, so here's band 7, and that just kind of looks like this, something like a weird washed out spy photograph or something that wasn't quite exposed correctly. There's definitely a lot of detail in here, but it's a little bit weird. And so band 7, remember, doesn't account for hardly anything in terms of like the variation in the data. And so we wouldn't want to use band 7 as our primary way to map geology for sure. Band 5 did have some value, 2 to 3%, almost 3% of the variance in the geology across the region. And we can see that, but it clearly was not as good as the first few that we looked at. Okay, so we've looked at those individually in a stretch format. Here's what it looks like in composite bands. But again, this is not good, right? It looks washed out all yellow. You can see some detail where there's fields from volcanoes, from alluvial areas, from mountains. But this is not what we want to see. And that's because we've stretched it wrong again. If we go in here, what we want to do is change it so it's, so that it's doing standard deviation stretch across all of these things. And now it immediately gets a lot better. We can see more detail. And it can get even better again if we go again down to 1 standard deviation. And now we see a lot of detail, right? We can see Tabernacle Hill from Pavant Butte, from the Cinders area, and these other volcanoes. They all look different. That's because they have different amount of weathering on them, different original rocks. This mountain range looks different than that mountain range. And this one, right? And then some of these dry lake beds and their salts show up differently than the alluvial fans. And so this is, if we're going to use just a straight up principal component analysis, 3 colors, where red is our PC1, green is PC2, and blue is PC3. That's what we want to do. So standard deviation of 1. This is a really nice stretch in detail. Now, I'm looking at the whole data set, right? But another option, like if you want to see more detail, so I'm going to zoom in to like these alluvial fans off of the side of the mountains that are coming over from the west here. And we can see like Lake Bonnell features and whatnot in these green and yellow colors. But I'm going to perform some magic here. We are currently stretching the data over the whole image, the data set. But if you switch the stretch to the local region or dynamic range, it's going to show you a lot of detail right there, which is going to help you see that, where the lake was. You see these etched shorelines, they come up only so high, is different than above the lake. That means the soils are different there because of waves eroding and depositing things. So we can see a lot of details that just weren't visible easily when we're stretching over the whole data set. So if you switch to dynamic range, you can map a lot of detail in here. Now it can get a little washed out when you go down to look at a different part of the image. But on the other hand, you can see different things then. So now we're seeing maybe different salt depositions in the Sevier Lake. And if we go to this mountain range and we zoom into here, we can see some things that might have to do with aspect differences, but there's probably real geologic differences in here that are really getting highlighted by using this dynamic range effect. Okay. I'm going to zoom back out, and then I'll zoom back into these volcanoes, and you can see very clearly this Tabernacle Hill where everybody goes and does caving through the lava tubes. It shows up very different than this younger volcano here. And then that younger volcano looks similar in color, but different than Pavant Butte. And this volcano over here. So we see a lot of detail in this principal component analysis. It's pretty good. The other thing, so PCA can be used really well to visualize those top principal components in red, green, blue, and create this psychedelic false color image, allowing us to map different lava flows, alluvial fans, soils, etc. And incidentally, it also shows really well probably which fields are fallow and not fallow. I think that purple is vegetation in this particular way. I've got the PCA set up. Vegetation is present. It seems like all the fields that are actively being productive are purple, and also the mountains with vegetation. And so the blue kind of is what we see in the lake beds, and those are clays and salts. And so those fallowed fields show up salty and clayey as well, blue over here as well. And we can confirm that, like if we look in some of these river beds, a lot of exposed sediments look similar, blue. Okay, so one thing to remember about the PCA is it's a just, visualization technique. I can interpret that this kind of pink purple is vegetation and green is a lava flow, but that's because I have a lot of knowledge about the area. It's not because the PCA tells me exactly what color equals what. It all depends on how you mix and match these, and it will probably look different if I switch band 3 to band 4, for instance. See what that looks like. Yeah, a little different. Now the fallowed fields are red, and the colors changed quite a bit as well. I did prefer band 3 to be on blue to see more variation. Okay, so how could we potentially use the PCA to maybe know a bit about what is going on more geologically? Now, remember, we input different soil layers. So band 1 was clay, band 2 is iron oxides, ferrous oxides was band 3, ferric iron, band 4, gaussins 5, ferrous silicates 6, and ferric oxides 7. A lot of iron involved. If we look back at the eigenvalues and eigenvectors, Okay, so the eigenvalues here, eigenvectors down here, we can see that relative to the first principal component, where most of the variance is, what is really positively correlated with that first principal component or negatively. So 5 is the strongest positive correlation, and 5 and 7. So 5 was Gaussons, which are kind of oxides, and but not iron oxides necessarily. And then ferric oxides. So oxides quite strongly in a positive relationship with principal component 1. And so it made sense maybe to have principal component 1 have been red, iron oxides. So cool. Really negatively correlated was 3 and 6. 3 and 6 are what? Ferrous oxides and ferrous silicates. Okay, so those would have been dark in the image, not, or low red. Okay, well, so what can we use with this? Well, also let's look to principal component 2, which had a lot of the variance too. And those ones, interesting, principal component 2 also liked band 7 of the input variables. And band 2, which was iron oxide. So oxides are really present. And band 3, it liked clays, iron oxides, etc. And so, if I go way down here where there's very little kind of correlation, things that show up are 6 input and 1, but that also showed up here. And so, this table could potentially help us see what are like the major input layers that are showing a lot of variance. And so the bottom line is we could decide which 3 of the input layers to show. So then we could have a more intuitive understanding of what's being shown in the geology. And so it seems that a good one to choose would be band 5, which again, band 5 was Gaussons, would be a good starting point. And so let's do that. So if we're going to briefly turn on the geologic composite bands, and right now it looks kind of weird because it is just on one standard deviation with bands 1, 2, and 3. And so what I was saying is that Gaussons could be shown as one of the colors. Okay, so if we go back here and go up to the correlation matrix, Gaussons 5, and Gaussons, what else do they correlate with? Oh, interesting, 7, right? So that makes sense because they also showed up strongly in principal component 1. So ferric oxides, Gaussons, and a little bit of iron oxides. So we could decide that we wanted to have band 5 in the piece. Ooh, sorry, I'm in the wrong one here. In the geocomposite bands. So these geocomposite bands are not the principal components. Band 1 is clay, iron oxides, band 5 is Gaussons. So, okay, I'm going to make band 5 Gaussins. Okay, now what else shows up strongly? I think we have to show clays because they're so different than everything else, and they do show up as pretty strongly related in principal component 3. Clay, I'm gonna like to show as blue, so I'll call that band 1 blue. And then amongst these other geologic things, I feel like we have to show silicates, and in a ferrous state make sense to be green. Okay, so this still doesn't look very good. Well, why? Again, we're on percent clip. We should move it to standard deviation. And let's not just do 1, but or 2, but let's do 1 standard deviation. Okay, so that's interesting. Maybe not as we want it, though. So it's pretty interesting. I would say that it's definitely not showing what we want in terms of the geology, like the PCA was. Let's go back to the PCA. We see a lot more detail than we do here. So going back to these geocomposite bands, I might have made the wrong choices in selecting things because I was kind of intuiting it more. I do still like clays, not only because they're strongly correlated with 3, but they're strongly negatively correlated with 2. But in 2, the big one that plays is so principal component 2 is band 2, which is iron oxides. I'm going to switch red to band 2 to get iron oxides. And I'm going to go back here, and then I'm going to go to green and change that to 5. Because that one, so 5 showed up, Gaussins showed up most strongly in PC1. So I feel like we have to include it. Most strongly in PC2, and almost most strong, well, so we're showing 2 as green. So sorry, confusing. Okay. Band 2 of the geology bands is iron oxides. We're showing that as red here. That was strongly related to both principal component 2 and 3. That's why we're showing that. Clay is shown as blue in the composite bands, and that was strong and seeming important. This is why clay is ubiquitous in this landscape, presumably. And then Gaussins showed up most strongly in principal component 1, so I've thrown it as green. And I'm quite happy with how this looks now, because I can see these different geologic areas look quite different from one another. And if we go into like these alluvial fan complexes, we can see a lot of detail in here. You then could say, okay, well, now I sort of know maybe what's going on, where we have a lot of blue, we have a lot of clay. If the blue is mixing with iron oxides, we get maybe more purple. And if it's more green, then we have Gaussins, but not a lot of pure green, but there's maybe a lot of mixed green. But for sure, it's a little bit more intuitive to interpret. Like, the volcano looks a little bit like the color of the volcano. But we can't really make it fully intuitive color-wise. But maybe more so than the PCA false color image. They're both false color images. So you'd have to decide then, which do you prefer to use? They both show differences really well. In some ways, maybe the geocomposite band that I made and selected is more intuitive than this to see difference, at least right here. But that might not be true up here in these mountains. Let's see. So this is the geocomposite band. And maybe you see more color variation with the PCA false color image here. And this all will, of course, get better if I switch this to dynamic range. So it already is on dynamic range up here. Now, if I turn on the geobands, you can see a lot of difference going on. They definitely look different than each other. How do they look compared to a geologic map? Then becomes a question. And so if we zoom in right here, where we have some different geologic units, brown, blues, and I'm sorry, I don't know what all these units are. Undoubtedly, there are probably some carbonates which is common in this area. This is the geo composites as opposed to the PCA. And I kind of feel like PCA is seeing like this little unit right here as compared to that pretty well. Maybe it's seeing it in the geocomposite that I made, but maybe not as well. And so the performance is variable. Over here in this mapped area, performance is not, you'd hope it would be really great because you got this nice stacked sedimentary rock layers going through here. But if you look at the GeoPCA, see a lot of purple. And remember that was a lot of vegetation. So that's really masking what we can see there. Same thing here, although a different color. And so some of the best places to check this presumably are here, right? Where we've got these different volcanic units clearly showing up different. Nicely mapped by both types of false color images. Okay, so some cautionary tales. These false color images, red, green, blue of the top principal components, or red, green, blue of various soil band ratios, stretched appropriately, can show you a lot of information. But the reality is, unless you really think about it hard, you are really just seeing difference as you go from this yellow here to this pink over here. But you don't know what rock is in the yellow and what rock is in the pink. You would have to ground truth that. So keep that in mind. We're doing remote sensing. What you could do next would be to go and ground truth things, find out what color means what, and then come back and run a classification on the band ratios or on the PCA components. And then you could get kind of an automated geologic map. A couple other things, we saw that the performance improved, right, as we zoomed in. Why is that? Well, we are looking at difference across a smaller area of values, so we're able to stretch out that geologic difference better. That is important to remember. A few other things that were complex in this area, we have a lot of vegetation, right? All this purple area on the kind of east side has got a lot of vegetation, and we're not really seeing through to the geologic units and the soils over there. And across this whole image, that's kind of important. It's probably also influencing the PCA analysis that we ran and the result that we got out of that. It could potentially be improved if we masked out the areas with a lot of vegetation. So one thing that we could have done would have been to first run like an NDVI as described in the chapter, normalized difference vegetation index, identified where the pixels were dominated by vegetation, removed those pixels from the scene, and then run the PCA only on the pixels that didn't have a lot of dominance by vegetation. And then I think we would have got an improved principal component analysis in the area of soils that are exposed. Wouldn't be influenced by those areas where we're not really seeing the soils. And the resulting image might have even looked better than it does. But hopefully you see the value in this and the fact that you could use this to begin to click out the boundaries of geologic units, whether they be rock or sedimentary and geomorphic deposits. Okay, so that's video number 4. In the next videos, in the coughing, we'll be looking at, there's one more, and well, actually, we've combined them. So video 4, we visualized geologic difference with the PCA. We compared a little bit to the geologic map, showing that it, is tricky, but it gave us a start. And we also looked at visualizing with select band ratios. Okay, so that is the video series for exercise 4.